All right, hello everyone, and welcome to lesson 1.7, which is really just a continuation of what we did in class, talking about summary statistics for a quantitative variable. We're still talking about quantitative variables right now. And make sure you've set up your notebook because you're going to be taking some notes. And we're really just going to sort of re-emphasize and add on to what we did in class for a minute, and then give you a chance to practice some. All right? Couple things. One, and we already took notes on this in class, so you don't have to add to your notebook, but just a reminder that standard deviation is something we will often use to talk about the variance or variation, sorry, not variance, the variation or spread of a data set of quantitative for a quantitative variable. If we're using mean to summarize the center, we often report standard deviation as well. And that standard deviation measurement reports how tightly the data values are clumped around the mean. The smaller the standard deviation, the more clumped around that mean the data is, the larger the standard deviation, the more spread out the data is. We'll talk about that a little more later. Now remember, really standard deviation is the square root of variance, and the variance calculation is up here. We did this in class once. You find the mean, then you subtract the mean from each of the data points, and you square each of those quantities, add them together, and divide by n minus 1. Take the square root of that, and we get the sample standard deviation. If we could do it for every individual, we would get the population standard deviation, sigma. Again, like those last two slides, we already talked about both of those things and took notes on them in class. Another reminder, to calculate the standard deviation, we find the mean, calculate the deviation of each value from the mean, the value minus the mean, square each of those, add them together, divide by n minus 1, and then take the square root. That takes us back to the original units. It'll always be greater than 0. The larger standard deviation means greater variation, and it is non-resistant. In fact, it's really non-resistant. All right, let's do another example of finding standard deviation. All right, first thing that we do whenever we are finding standard deviation by hand, and we will have ways to do it on a calculator later, but as you saw in the first meme, we like to do things the hard way sometimes at the beginning here in statistics. We first need to find our mean, right? And a mean, how come this guy's not right? Let's do this, there we go. Our mean we find by adding together and dividing by the total number of data points. So 0 plus 1 plus 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 4 plus 5 gives us 23. And we're going to divide that by the total number of data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, divided by 10. And this data set is talking about from a sample, asking high school students how many siblings they have. And it looks like the mean here is 2.3 siblings. All right. So we find the mean, and then we need to find the deviation from each of the data points from the mean. So this is kind of the time-consuming process here. We have to do 0, which is our first point, minus 2.3, and then we will square that. So if you like to, some people like to actually list out all the variance first. You would do 1 minus 2.3, 1 minus 2.3, 2 minus 2.3, 2 minus 2.3, 2 minus 2.3, and so on and so forth. I want to speed things up because after you've listed out each of the variances, you square them and you add them together. So 0 minus 2.3 squared plus 1 minus 2.3 squared. But there are two of those that'll happen, so I'm going to go ahead and say 2 times that. Plus 2 minus 2.3 squared. And I would do that 1, 2, 3 times. I could add it 3 times, or I can just say 3 of those. Plus 3 minus 2.3 squared. And there are 2 of those, so I will add that. That got a little ugly, so let's erase that. Make that a little neater. Plus, and there were 2 of those data points that are here at 3, plus 4 minus 2.3 squared. There's only one of those, plus the quantity 5 minus 2.3 squared. So again, what we're doing, we're finding the variance or the deviation of each data point from the mean. So the value minus the mean, we square it, and we add each of those up for all the data values here. I'm using coefficients here because some of the data values are repeated. Instead of writing out plus, 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 I'm just multiplying. And then we divide that, whatever that number is, by the quantity in minus 1. All right, and this is going to give us that variance there, that variance, which some people refer to as s sub x squared. In this case, n minus 1, what is n minus 1? N is the number in our sample. There were 10, we said, in our sample. So we're going to use 10 here, 10 minus 1, or 9. Right. So this is kind of the tedious part. We add all this stuff together, and then we'll divide by 9. Now, if we go ahead and do that on our calculator, we'll find that the variance here, if you type all those things into calculator, add them all up, will give us 2.23 repeating, if I've done my math correctly. All right, 2.23 repeating should be our variance. All right, then we take that variance, and the standard deviation is the square root of that variance. So our s sub x, our standard deviation here, is going to be the square root of 2.23 repeating, which is going to be about, let's round this to 3 decimal places, 1.494 will be our standard deviation. And you might go, well, what are the units of standard deviation? Well, the units of standard deviation are whatever the units of the thing we're measuring is. So this would be, the standard deviation is 1.494 siblings, is really what we're saying here. All right? If you think about that, that actually means that up here, this number here is siblings squared. All right? We're going to talk a little more about units here in a moment. But the standard deviation is 1.494 siblings for this sample. That's the sample standard deviation. All right. Recap. Find the mean, find the deviation of each value, square those, add them all together, divide by the number of individuals minus 1, and then take the square root of whatever number you find. All right. Cool. Here we go. So let's talk a little bit more about standard deviation. Standard deviation is a really important measure. It measures the variability. Think about the larger standard deviation. A large standard deviation means that the data have more variability. So for example, in here, the red and the blue graph actually have the same mean, but the standard deviation of the red graph is bigger. That's because the red graph is more spread out. The blue graph, more that it is clumped closer to that center. All right. We could also actually have an example where we have, I don't know, a situation where maybe our graph actually has more data points on the outside than the inside. And if that was perfectly symmetric, we might have the same mean here. This black graph would actually have a big standard deviation compared to the blue graph because it has more data points out on the edges. The smaller standard deviations will happen when the data is peaked right there really closely to the mean. If we have something nice like this blue graph where it's peaked right around the mean, pretty tight in, we have a smaller standard deviation. If we have lots of data points farther away, the standard deviation, the variability, will be greater. All right, the variation or variability of that data will be greater in this black graph or in this red graph, okay? You'll often see these kinds of standard deviations reported with data just because it gives us a pretty quick measure of how much things are varying within the data set. Another observation, units and statistics. Units are really important, like they are in most classes. If you change the units of measurement, let's say for some reason we change the units of measurement from siblings to like half siblings. That's probably weird because we don't typically do that. Let's say we're taking some measurement of like distance you work from your home. We measure it in miles versus kilometers. If you change the units of measurement, the calculated statistics are going to be affected as well. But that makes sense, right? If you're measuring things in miles, then all of your means, medians, standard deviations will be in miles. But if you're measuring in kilometers, it'll be in kilometers. This becomes extra visual when we talk about like remembering that variance is squared. So if we're talking about like square miles are actually considerably different than square kilometers. Just the way that we multiply things together makes square miles that much bigger than square kilometers. So don't just willy-nilly change units of measurement, okay? Let's talk a little bit more about outliers. There are many, many methods for determining outliers, and there's no one that is per se right, but two are most common. One, people will say that an outlier is any value greater than the third quartile plus 1.5 times the IQR, or value less than the third quartile. Oop, that should not say third quartile. That is not right. A value less than the first quartile minus 1.5 times the IQR. Again, think order of operations. So you multiply 1.5 times the IQR and add it to Q3. Any numbers bigger than that are upper outliers. Take 1.5 times the IQR and then subtract it from quartile 1, and that will give you any lower outliers, anything less than whatever that number is. Some people will also use this. If we have standard deviations, many people will use that an outlier is a value 2 or more standard deviations above or below the mean. Let's take a look. Remember that data set from the U.S. women's national team? Well, here it is again. We'd already calculated the median. We calculated the Q1, calculated the Q3 in class. We calculated the IQR in class. So we actually have all the stuff to determine what might be outliers. So the low outliers we would calculate like this. We have 1.5 times the IQR was 3.5. Ooh. Times the IQR was 3.5. So if we do 1.5 times 3.5, and we subtract that from Q1, which is 1. So 1 minus whatever that product is, will take us down to negative 4.25. Are there any scores less than negative 4.25? No. So there's no lower outliers. Our upper outliers are going to be greater than 4.5, which is our Q3, plus whatever that 1.5 times the IQR is. So 4.5 plus 1.5 times the IQR. Turns out that that number is 5.25. So 4.5 to the quarter 3 plus that quantity, 1.5 times the IQR, will give us 9.75. And there is a data value bigger than 9.75. So the game in which the U.S. women's national team scored 10 goals appears to be an outlier. We can make that argument. We can now say is an outlier using this strategy. It is important to identify outliers because of the meaning and the impact. So an outlier might represent some extraordinary occurrence, which could be interesting to investigate. If you realize something extraordinary is happening with a specific data point, it's probably worth, as a scientist or an engineer, figuring out what's going on. Additionally, the impact of outliers, as we've seen, can be great because outliers can greatly impact things like the mean or the standard deviation. So it's nice to find those. The second way that people identify outliers is by first finding the mean and the standard deviation, and then from there saying, okay, are there any data points that are 2 or more standard deviations away from the mean? Remember, we got to think about the mean here. If we have a really nice symmetric data set, again, this is assuming best case scenario, if we have a pretty nice symmetric data set, and we have a mean, the standard deviation you can kind of think about is, well, how clumped is it around the mean? One standard deviation might be out here. A second standard deviation away from the mean might be out here. So we're basically saying anything at or greater than that second standard deviation away from that mean is possibly going to be an outlier. We'll talk about more about that stuff later, but generally speaking, it's a strategy that works like this. We find the mean, then we say plus 2 times the standard deviation is 8.19, and then 3.15, that's the mean, minus 2 times the standard deviation will take us down to negative 1.89. And we say, hey, are there any things at or greater than those values? All right. Nothing less than negative 1.89. We don't have to worry about that. But look up here. There are actually 2 data points using this method that we could identify as outliers. The game's 9 and 10 points scored are outliers using this method. And this is where we start to realize that statistics is kind of subjective. There's not necessarily a way to do something. We actually have some choice. And the choices we make might impact greatly how trustworthy our answers are. In this situation where our data is really skewed heavily right, and we have our median and stuff like pretty close to 1, using mean is not great because, right, mean is not resistance. Our mean is going to be pulled out here. This is not a particularly symmetric data set. So the standard deviation method here might not actually be great. We'll talk more about this stuff as we go throughout the year, but these choices are ultimately important. But those are the two different methods for identifying outliers. IQR, 1.5 times the IQR, or 2 or more standard deviations away from the mean. Quick recap here on resistant versus non-resistant. Our main resistant measures, statistics, are the median and the IQR, and the stuff kind of related to those things, like the first quartile, third quartile, things like that. The non-resistant measurements, statistics, are means, standard deviations, and ranges, because all of these are heavily impacted by outliers. All right, to close out, I want you to practice. There are 5 problems in the textbook I want you to practice. This is not part of the optional homework, 5 questions in the textbook to practice. Check your answers, and once you're feeling okay, then go ahead and complete the check-in quiz 1.7. That will be in the near pile. All right? Take care, everyone.